Hey guys, welcome back to another video, and today we're going to be taking a look at the LeetCode question, concatenation of consecutive binary numbers. Alright, so in this question we're going to be given an integer n, and we want to return the decimal value of the binary string form by concatenating the binary representations of 1 all the way through n in order modulo 10 to the power of 9 plus 7. Okay, so what exactly does this question mean? So to better understand it, let's just go over here. And over here, we're going to have a n value of, let's say, 3. So the question itself is pretty simple. So let's just first go through what it's asking for, and then we'll see how we can solve it. So when n is equal to 3, the numbers that we're focusing on are going to be 1 all the way up to n, including the number 3. So in other words, in this condition, it's going to be the numbers 1, 2, and 3. Now the question is, what exactly do we do with these numbers? So over here, we're going to have some sort of a string, or let's just call it a result, and res over here is going to contain the concatenated values of each of these numbers' binary representation. So what exactly does that mean? So we're going to start off with the number 1, okay? So the number 1 over here, what exactly is the binary representation of the number 1? So real quickly, if you don't know how it works, so binary representation is also known as base 2 numbers, and our normal integers are base 10 numbers. So what exactly this means is, for example, let's say we have a number which is 1010. What is this going to be in binary? So in binary, this is going to be 2 to the power of 0 multiplied by 0, which we get from over here. Then we're going to add this with 2 to the power of 1 multiplied by the value over here, which is 1. Then we add that with 2 to the power of 2 multiplied by 0 plus 2 to the power of 3 multiplied by 1, since we have a 1 over here. So this is how we're going to kind of unpack this binary value over here and get it into the decimal or integer form. Okay, so this over here and this over here gives us a value of 0, and this gives us a value of 2, and this over here gives us a value of 2 to the power of 3, which is 2 times 2, 4, 4 times 2, 8, into 1, which is 8. So this over here, 1010, is nothing else but the number 10 itself represented in binary. So this is how binary representation works. And now let's see what would be the binary representation of 1. So the binary representation of 1 is going to just be the number 1. So in other words, 2 to the power of 0 multiplied by 1, which is, well, 1. Okay? So we now have the binary representation of 1. Now we want to get the binary representation of 2. So the binary representation of 2 is going to be 1, 0. So like we saw earlier, it's going to be 2 to the power of 0 multiplied by 0, which is 0, plus 2 to the power of 1 multiplied by 1, which gives us 2. So we're going to take this 1, 0 and concatenate it to this kind of result string that we have. So now we're going to end up with 1, 1, 0. Perfect. Okay, so now we have this. And finally, we have the last number, which is 3. So 3 over here is going to give us 1, 1. So the binary representation of 3 is 1, 1. So that's 2 to the power of 0, 1, plus 2 to the power of 1, 2. So 2 plus 1, 3. So now we add 1, 1 to our result. So this over here is going to be the final result that we have. But now all we have left to do is we want to convert this into an integer value. And to do that is the same steps like I showed you earlier. And I think this over here gives us a value of 27. And 27 is going to be the answer that we end up outputting for our final solution. Alright, so now that you understand what the question is, so what I just showed you is one way to do it. We can kind of go step by step and kind of add it to some sort of string and then convert the final value we get into an integer value. Now one thing you do want to notice is once we get the number 27, we want to be doing 27 mod 10 to the power of 9 plus 7, okay? And then we output that answer. So in this case, when you do that, you'd actually just end up with 27, since 27 is a lot smaller than this number over here, okay? But yeah, this is one thing that we do want to do before outputting the answer. So now let's try to understand how exactly we can solve this in a lot more efficient and simpler manner using bitwise operations. Alright, so over here, I kind of just want to show you a pattern that we want to kind of notice. And to do so, I have the numbers 1 all the way through 8 written out over here. And below them over here, I want to write its binary representation. So 1 in binary is just going to be 1. 2 in binary is going to be 1, 0, then 3 is going to be 1, 1, and 4 over here is going to be 1, 0, 0, and I'll fill out the rest of it. Okay, so over here we have everything else filled out, and the thing that I really want to show you is over here, the length of the binary representation is just 1, right? So over here, the length of the binary representation is 1. Now when we move on to 2, the length of the binary representation over here is 2. And it remains 2 for the next number as well. But when we get to 4, the length of the binary representation becomes 3, and it remains at a length of 3 for 5, 6, 7 as well. And for 8, it now changes a length of 4. Now, why exactly does this happen? Is there any sort of way that we can explain this? So to do that, let me just actually rewrite this in a simpler way. So 1 is nothing else but 2 to the power of 0. 2 is nothing else but 2 to the power of 1. And 4 is nothing else but 2 to the power of 2. And 8 is nothing else but 2 to the power of 3. So as you can see, the idea is pretty simple. If there is some sort of number where 2 raised to a certain integer gets us that number, then in that place, the number of values or the length of our binary representation is going to increase by 1. So in other words, if you're familiar with how logarithms work, log base 2 of whatever number, let's just call it n, has to be some sort of integer. And when that is the case, then we're going to go to the length and we're going to increase it by 1. So what do I mean by this real quickly? So in the beginning, let's say our length is equal to 0. Okay, now we go to the number 1. So when you do log base 2, 1, we get a value of 0, which is an integer. And in that condition, we're going to increase the length by 1. And that's correct because the value over here has a length of 1. Now that we go to 2, in this case, log base 2 gives us a value of 1, which is an integer. So now the length increases by 1, giving us a length of 2. Now, when we do log base 3, we're not going to be getting an integer. So in that case, the length is going to remain the same. But again, now when we go to log base 4, we're going to increase the length by 1, and we're also going to then increase the length by 1 when we get to 8. So this over here tells us what is the length going to be of the binary representation. So this is one thing that we want to keep in mind, and we're further going to simplify this later on. So just remember how this is being done, and now we'll see how exactly we're going to apply it. Okay, so over here we'll see how exactly we end up applying this. So two things that we're going to be keeping track of is going to be the length, and another thing that we're going to keep track of is going to be the result itself. Now the result is actually just going to be an integer value, and we're directly just going to deal with the integers. But just for the sake of understanding, I'll also write down the binary representation of this on the right hand side just so you can understand how it's working. So over here, let's take n is equal to 4 as our example. So what does that mean? That means we go from all the numbers to 1 through 4, we concatenate those binary representation values, and then convert that to a decimal value, okay? So n is equal to 4, and let's see how that looks like. So in the beginning, we're going to have our result to be equal to 0. Its binary representation is well going to be 0, and the length over here is now going to be 0 in the beginning. Now again, so for 0, you could write 0 or you could write 0, 0, 0. It doesn't matter, okay? So now keeping that in mind, what exactly are we going to do? Now the first step is we go to the number 1, okay? Because we want to go all the way from 1 to 4. So when we are at 1, we want to see, do we increase the length? And the answer is yes, because 2 to the power of 0 gives us 1, or in other words, log base 2, 1 is an integer value, so we increase the length by 1. Now this tells us that the length of whatever the binary representation of 1 is going to take up a length of 1. Now keeping this in mind, what we're going to do is we're going to perform a left shift for that many spaces. So that should be more clear on the next step, but so in this case, I'm not going to perform it since it's the first iteration. So over here, we're going to add the binary representation of 1, which is 1, to our binary number over here. Now how exactly are we going to add it? So for kind of adding them, we're going to be using the bitwise OR operation, and it's shown with this operator over here. I think that's called pipe. I'm not too sure, okay? So in this case, how that works is as long as we have a 1, we're going to output a 1. So for example, if we have 0 or 0, we get 0. But in every other condition, 1 or 1, 1 or 0, 0 or 1, we're going to end up outputting 1. So in this case, what is our new value going to be? So we're going to do 0 or 1, and we're going to get a value of 1. So that is going to be our binary representation, and we want to convert this to an integer just for keeping since that's really what we want to end up outputting. So 1 in binary is going to be 1 as an integer as well. Okay, perfect. So now let's see what the next step looks like. So now we have 2. Now first we want to see, is the length going to increase? And the answer is yes, because log base 2 is an integer, so the length is now going to be 2. And you can also see this. Now the length went from 1 to 2. Okay, and the binary representation of 2 over here is 10. So one thing that we need to do is when we're accounting for the 10 over here, and when we're adding it to our binary number, we want to move this to the left by that many steps. So for example, if you just did 1 or 1, 0 right now, we wouldn't actually end up getting a proper value. So we want to make space accounting for these extra length of 2 worth of binary values. So to do that, we're going to left shift it. So in other words, we move it to the left by 2 steps. So we move 1 to the left by 2 steps, and the steps on the right are going to be filled with zeros, okay? So how that's going to look like, it's going to be 1 and then 2 zeros on the right of it. Now with these 2 zeros, we need to perform the OR operation with the bitwise representation of 2, which is nothing else but 1, 0. So now we have 100, so 100 or 10, which gives us 110 as the output. So this is our new binary number, and now let's convert this to our integer, and that's going to give us the number 6. And again, just to kind of be clear, we're only going to be keeping track of the result or the integer itself. I'm just showing the binary representation so you can understand. So now let's just go through this a little bit faster. So now we have the number 3. So is the length going to increase? And the answer is no. And in that condition, we're now going to left shift it by 2. So 1, 2. And now we account for 3, which has a binary representation of 1, 1. So now we have 1, 1. And to this, we're going to be performing the bitwise OR operation, which gives us 1, 1, 0, 1, 1. Okay, so that's now what we end up with. Now, after we go to 3, the last number we have is 4. But one thing that happens is at 4, we now have a length of 3. So we increase the length by 1, and it's now going to have a length of 3. And again, by the way, sorry, I forgot to do it earlier. The result is now going to update to 11011, which in decimal is nothing else but the number 27. Okay, so now we have the number 4, and we already took care of the length. And now, how exactly do we account for it? So we want to move the binary values to the left by 3 steps. So the reason it's 3 is because, well, the length is 3. So now we do it 1 time, 2 times, and 3 times, giving us a total of 3 left shifts. So now we need to account for this number over here, which is 100. So we have that over here, 100. Perform the bitwise OR operation, and what you end up with is the only thing that changes is now we have, so this over here becomes a 1, and the rest of it 00. And now we convert this binary to our integer over here, which is going to give us a integer value of 220, and this is what we're going to end up outputting. Now again, just to be clear, we're not going to be keeping track of the binary values. I'm just using it as a way to show you what is happening behind all of this, okay? So now hopefully you understand the concept, and one thing that we do want to make sure is we know we're increasing the length by 1 when log base 2 of a certain number, in this case, is going to be equal to 1. But we can actually simplify this furthermore. So if you actually observe, you should be able to find a small observation. So when there is a change, what's going to happen is, so there's a change in numbers or length in between 1 and 2. Similarly, there's a change between 3 and 4, and between 7 and 8 over here. Now over here, we're going to have another operation called the bitwise AND operation, and you denote it using the ampersand symbol, so this. So how this works is when you do 0 and 0, you're going to get a value of 0. When you do 1 and 0, you're going to get a value of 0. 0 and 1 also gives you 0, and the only condition where you get a value of 1 is going to be when you do 1 and 1, and in that condition you get a value of 1, okay? So now keeping this in mind, what exactly can we actually see as some sort of pattern? So in this case, we're going to perform the AND operator between whenever the length is changing. So at 1 we have a length of 1, and at 2 we have a length of 2. So we're going to do 1 and 1, 0. So when you do 1 and 1, 0, we end up with a value of 0, 0, okay? Now simultaneously, when you do 3 and 4, because 3 has a length of 2 and 4 has a length of 3, so in this case, the value right before 4 is at a different length. So keeping that in mind, when we do this AND operator between 1, 1 and 1, 0, 0, we end up with the value 0, 0, 0. Okay, so just to kind of show you the pattern one last time. So over here, if we perform the AND operator between 8, which has a length of 4, and right before that 7, which has a length of 3, we're going to have 1, 1, 1, and 1, 0, 0, 0, which gives us 0, 0, 0, 0. So all of these 0, 0, 0, 0, 0, or 4 zeros in a row, all equate to 0 when you convert it to an integer. So this is the basic idea. So when there is a change in length, the number before it, when you perform the AND operator with it, is going to give us a value of 0. So instead of using the logarithmic method, this is one way that we can find the answer. And this is what we're actually going to use since it is going to be a lot faster. Okay, so now let's take a quick look at how the code is going to look like. Alright, so let's start off by looking at the Python code solution to this. And just remember that, like it says in the question, we want to find out the binary representation of 1 to n in order modulo 10 to the power of 9 plus 7. So we do need to account for this, so I'm just going to copy it over and we'll account for it in our code. Okay, so let's just store this in some sort of variable and we'll just call it mod, and it's going to be equal to this, but instead it's going to be 10 to the power of 9 plus 7. Alright, so now that we have this stored, we need to have a few more variables. So one variable that we're going to have is we need to store what is going to be the length of a current bitwise representation of a specific number. So this is the length of the bitwise representation, and that's going to start off at 0. And the other variable we want is going to be the result itself. So both of these are going to have a value of 0 in the beginning. Alright, so now we're going to go inside of a for loop. And what exactly is this for loop going to be for? So for I in range, we're going to start off at 1 and we're going to go all the way up to n including n. So since we want to include the value n, we're going to do n plus 1. Okay, perfect. So now we have our for loop. Over here, we're going to check if we need to increase our length or not. Now again, remember, what is the condition of when we need to increase the length? So like I showed you earlier, we could do math.log and check if it is an integer. So math.log dot is underscore integer, and using that method we could find out whether it is whether the length is going to increase or not. Or like I showed you, you could use the AND bitwise operator. So you would do if I and the previous number, whatever the previous number is. So if I and I minus 1 is equal to 0, then in this condition over here, that means that we need to increase the length by 1. So now the length is taken care of. Now what exactly do we have left to do? So the thing that we have left to do is we want to concatenate this value onto our existing result. So to do that, our result is going to be equal to result. And the first thing we want to do is we want to left shift it. Now, how many times exactly are we going to left shift it? And that is going to be defined by the current length that we have. So first thing we're doing is we're taking our result and we're performing the left shift operation on it with whatever length we have, okay? And by doing this, we're going to have an empty space for us to concatenate the current value we're on. Right, so now that we have this, we need to actually add the current value that we're on. And how exactly are we doing that? So we're doing that using the bitwise OR operator. So we get that by using this symbol over here, and we're going to do it with I, okay? So all of this over here gives us the value, but we want this in the order of this mod this value over here. So let's just perform that. So this mod by this value over here, 10 to the power of 9 plus 7. Now that's all. Okay. Now all we have left to do is we want to return our result at the very ending, and that should be it for our solution. All right, so now let's take a look at the Java solution. And before doing so, just remember that we want to give out an answer of the binary representation of 1 to n in order modulo 10 to the power of 9 plus 7. So we do need to account for the in order modulo 10 to the power of 9 plus 7. So let's just store that value, and we're going to keep using that value. So over here, let's just do int mod, and this is going to be 10 to the power of 9. So 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then plus 7. So this is going to be 7 over here. So now that we have this value, we need to define two more variables. So one of them is going to be the length, and the length over here is going to be the length of the binary representation of a certain number, and it's going to start off at 0, and we keep increasing it when we have when it actually meets a certain condition, and we'll go across the condition once again. So now we need to define our result variable and this is going to be the actual answer that we end up outputting. So over here we're going to do long and result is called res, and it's going to start off with a value of 0. Okay, so now we're going to go inside of a for loop, and inside of the for loop, we're going to start off with a value of 1, and we're going to go all the way up to and equal to n, because we want to go 1 to n, including the value n itself. And at each iteration, the value is going to increase by 1. Okay, so now once we're inside of this for loop, one thing that we want to consider is how exactly is the length going to change. So to keep track of that, we're going to have an if condition, and the condition is that if whatever value we're currently on, and when we perform the AND-wise operator, so I and I minus 1 is equal to 0, then in that condition, we know that we are increasing the length by 1. So in this case, we need to increase the length by 1, so it's going to be length plus plus, and yeah, so now our length has been increased by 1, and now what we need to do is we need to actually change the result itself. So the result is going to be equal to the result, and the first thing we want to do is we want to left shift it. So res left shifted, and by how much do we want to left shift it? So that's going to be given by the length that we have. So after left shifting it by how much, whatever the length is supposed to be, by then we've made up enough space for concatenating or adding the current number that we are on, which in this case is going to be the number I. And like I showed you earlier, the way we're going to be kind of adding this on is going to be by using the bitwise OR operator. So bitwise OR with the current number, which is I, and over here we're going to perform the modulo operation with this value over here. So mod. Okay. Perfect. So now that we have this, the last thing that we have left to do is we want to return our result over here, and that should be it for our solution. So sorry about that. So one thing that we need to do is before actually submitting this, we need to convert this into an integer. So let's do that, int res. Okay, so let's submit this now, and this should get accepted. So now let's talk about the time and space complexity. So the time complexity is going to be big O of n, and the reasoning for that is pretty simple. We're only looking at the numbers from 1 through n. So if you look at the for loop, we're just going from 1 through n, and that's it. So that's going to be the time complexity, big O of n. And for the space complexity, it's going to be constant space or big O of 1, since we're not using any sort of extra space that we need to use. So that should be it for the video. Do let me know if you have any questions, and thanks a lot for watching.